So today we will be discussing on bitonic sorting network. Now same as we did in the earlier case, here also we will be first defining what is bitonic sequence. Then we will be discussing bitonic merge. Then you will be discussing bitonic merging network. Finally, we'll have bitonic sorting network. So let A1, A2 be a sequence. A1, A2, A2n be a sequence. Now the sequence is bitonic sequence. If there exists a J such that either A1 less than equals to A2 A2n or by some cyclic shifts it satisfies one. Right? The sequence is known as bitonic sequence if either A1 less than equals to A2 less than equals to AN less than equals to AJ greater than equals to AJ plus 1 greater than equals to A2n, or by some cyclic shifts it achieves this one. Now for example, a sorted sequence is a bitonic sequence. Okay? Say why it is so? 1, 2, 3, 4. So by cyclic shift you can get 2, 3, 4, 1 which satisfies your proof. Similarly, that 4, 3, 2, 1 also a bitonic sequence. Right? This operator, even though I have written less than equals to, it can be greater than equals to also. By cyclic shift you can show that one. Another thing what I can tell, a sequence of two elements is also a bitonic sequence. A sequence of two elements is a bitonic sequence. Okay, the definition is clear. Any ambiguity at this stage? No. Yes or no? Yes. Now, if it is clear, then you can define a theorem. Let A1, A2, A2n be a bitonic sequence of 2n elements. Define two sequences D and E as where Di is minimum of Ei and An plus I. Ei is maximum of Ei and An plus I. Then D and E are bitonic sequences. Maximum of D is less than equals to minimum of E. The maximum elements of D is less than equals to minimum of E. So statements are clear that what we have obtained the two sequences D and E. D is obtained, the ith element of D is obtained by taking the minimum of these two elements, and Ei is obtained by taking the maximum of these two elements. Then D is a bitonic sequence, E is also a bitonic sequence, and maximum of D is less than equals to minimum of E. Now, how, in what way this can be used for your sorting? See, what it gives you that from this sequence A, you are making the two sequence, one is D and another one is E, right? From this two sequence, you made D and E. Now this, recursively you do the bitonic merge on that, recursively do the bitonic merge on this, and you get another subsequence like that. And every time you are achieving one thing, that these elements are smaller than these elements. These elements are smaller than these elements. So by some recursive method, if you can sort this one, if you can sort this one, then the element becomes the sorted one. Is it okay? So that's the idea. Now how to prove this theorem?
We can take three cases.
You take three cases.
Wherein the bitonic sequence changes its increasing or decreasing halfway, before halfway or after halfway.
Could not get you. You have
J equal to n.
J equals to
J less than n, J equal to n.
J equals to n, J less than n,
And J greater than n.
J greater than n.
Prove it separately for these three cases.
Yes. So, first thing is that the cyclic shifts of the sequence A will affect both the D and E sequence similarly? Huh? Without affecting the property of these two properties? If you do the cyclic shift, it will affect both the sequence, D and E, right? Agreed? But it will not affect these properties, right? So we assume that for simplicity, we assume the sequence is satisfying this type of characteristics. First, this assumption we are making. Okay? Now, second part is that as he mentioned, the j can be less than equals to n, j can be greater than n. Right? Now, both the case, if it is less than n, I can see from this direction that this j becomes greater than n. See, if I look from this side, agreed, you understood. If j is less than n, if I see from that side, j becomes the greater than n, and that becomes also bitonic sequence. Only less than symbol it becomes the greater than equals to symbol. Nothing else. Right? So without any less of generality, we assume that j is greater than n. We assume j is greater than n. And if I can show this one, the other one is also you can show. So you assume that j is greater than n. So you have a1 less than equals to a2 less than equals to an less than equals to aj plus 1 a2n. Now, up to this we have done it, and this side it is less than equal, this side it is greater than equal. Right? Now, assume first case is there are two possibility. Case is an less than equals to a2n, and another case could be an greater than a2n. These are the two possibilities you have. This is an less than equals to a2n, or an can be greater than a2n. Now let us assume that an greater than equals to a2n. First case. In that case, what is your di and ei? Di is what? Minimum of ai and an plus I. So what is that ai and an? Who is the minimum? Yeah, there is no ambiguity, yes. So I can write ei. And what is ei? A n plus I. Agreed? Basically, this becomes your D sequence, this becomes your E sequence. Yes. So this satisfies D1 less than equals to D2 less than equals to Dn, and E1 is less than equals to E2 less than equals to yes, because this side is E1 less than equals to E2 Ej minus n, and then it is greater than. So this is a bitonic sequence. This is also a bitonic sequence.
So why is the minimum always A? What
For this case, here A1 less than equals to A2 less than equals to AN greater than less than equals to this greater than equals to and so on. Right? Now this element, this is your AI, and corresponding element is maybe here. Suppose corresponding element is here, AN plus I, right? Now if it is the case, so this is less than, so this is larger than this one, so minimum becomes DI and maximum becomes EI. Another possibility is that your AI is here, AI plus what? AI is here, AN plus I is here. This element is less than this element. This element is less than this element. This element is less than this element. So this element is less than this element. So this becomes DI, this becomes CI. Agree? So this becomes D sequence, this becomes E sequence, and both of them are bitonic sequences, first part. Second part is the minimum of, maximum of D sequence is Dn. Maximum of D sequence is Dn. Minimum of E sequence is what? Huh?
Either E1 or E2.
Yes. Minimum of E1 or En. Right?
E2.
Huh?
Oh, sorry.
En. Now, A1 is either E1. E1 is what? E1 is your AN plus 1 and En is your A2n. Agreed? Now, if it is the case that and Dn is your An, you already have shown, or from the definition, that An is less than or equals to N plus 1. From the definition itself, because J is somewhere, this is your N and this is your J. This element is always greater than this element. And also, by this case, this element is greater than this element. Agreed? So Dn is always less than or equals to En. The next case is, if I can show for this case also, then your problem is solved. This is given to you. Now I can always find out a K. In such a K, such that A I can always find out a k such that ak minus n less than equals to ak and ak minus n plus 1 greater than ak plus 1. Now, how can you justify this? What I have found that aj minus n is less than equals to aj. This is given to you. Agreed? aj minus 1 is less than equals to aj because from the definition of your bitonic sequence. Yes. Now you look for aj minus n plus 1 whether it is greater than aj plus 1 or not. Suppose this is your j minus n and this is your j. So this satisfies the property, this is less than equals to this. Now whether this element is larger than this element. Suppose it is not. That means this element is less than equals to this element. You look for the next one, whether this element is larger than this element or not. Not. Suppose no. But in that case, think about this one, n minus 1 and 2n minus 1. So this element is less than equals to this element. Right? Because you are going one by one. So you got the last case, an minus 1 is less than equals to a2n minus 1. But from the assumption an is greater than a2n. So you will get one k satisfying this criteria. I am looking for the first such k. I am looking for the first such k. We are looking for the smallest k satisfying this criteria. Right? Yes. Clear? Yes or no? Clear. If it is clear, then you got this is n, this is j, this is k, this is k minus n, this is 2n. Now here you have the three cases about your ai and an plus I. I can be, n plus I can be here, can be here, can be here. Okay? Okay? I can be here, I can be here. So I can be here, here or here. Agreed? Now suppose I is here. First case is I is here. So what should be the and this is your j, this is your k, and I is here. N plus I is here, and I is here. This is the first case. If now you tell me what should be your di and what should be your di in this case when I is n plus I is here. Di is di is ai and ai is and also in this zone, while I am in n plus I is lying in this zone, can I write di is less than equals to di plus 1 and ei is also less than equals to I plus 1. I can write this. I is less than equals less than this number. Not crossing that number, huh? Crossing the I can write here I plus 1 is less than. I plus 1 is less than equals to j plus 1. that condition you put. Right? So that up to this point I am talking. Is it okay? Yes. Now let us take the second case. N to N. This is your J, this is your K, and this is your K minus N, and N plus I is lying here. N plus I is lying here. Now, can you tell me when N plus I is lying here, N minus I is lying here, what is your DI and what is your DI? Huh? DI and? So, in order to show that, you will be writing like that, A N plus I is greater than equals to A N plus I plus 1 greater than equals to AK. AK is greater than equals to AK minus N greater than equals to Basically, I am going from this direction to this, then from this to this. I have used this property. Right? So you are writing di is your AI and ei is an plus I. Right? And what is the relationship between di and di plus 1 here? Di is and what is ei? Right? So you got the second case. Now I need the third case. Third case is your J, your K, K minus N, your I is lying here. So I is here. Now you see, here I can write AI plus N is less than equals to AI plus N minus 1 AK plus 1 less than AK minus N plus 1. So it is here. Less than equals to AK minus N plus 2 AI. Agreed? Basically what I am doing, I am moving from this side to this side. Here it is K plus 1 and then moving from this to this. From this side to this K plus 1, and I know the relationship from between K plus 1 and K minus N plus 1. I am moving from this to this. Is it okay? If it is okay, then here I get this relation. From there I can get DI and EI. What is DI? A N plus I and here AI. Right? And what is the relationship between DI and DI plus 1? EI and EI plus 1? di a
Greater than equal to
di is greater than equals to, because yes, because di plus 1 will be here. So this will be greater than this. And ei? 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 Why? See, ei is coming this side, right? Ei is this one. Ei is this one, ei plus 1 is this. So, ei is isn't it? This is ei. This is ei plus 1. So if I combine all these, what I get? First, let us consider D1 case. You get D1 less than equals to D2 less than equals to dj minus n less than equals to dj minus n plus 1 dk minus n, then I don't know the relationship here, dk minus n plus 1 right? I don't know, because here it ends up to dk minus n, and this side I am starting from dk plus n minus 1. I don't know that relation. What will be the relation? So the relation, we will find out what is the relation later on. Up to this is known to you. What about E1? E1 is less than equals to E2 less than equals to Ej minus n, then you have greater than equals to Ej minus n plus 1 greater than up to Ek minus n. I don't know the relationship between Ek minus n and Ek minus n plus 1. Then I know this relation. Do you know any relationship between E1 and En? What is the relationship between E1 and En? What is your E1? E1 is?
yes, then.
What is E1? Huh? An plus 1. E1 is your An plus 1. What is your En? En is where? Right? If it is, do you know any relationship between E1 and En? So I can write En is
Less than.
En is
Less than.
sorry, agreed? Yes. Now, in that case, first you tell me, if I know all this, so I know the relation here, En less than equals to E1. So think about this one. Can I tell that this is a bitonic sequence? Irrespective of whatever the relationship between these two. Suppose it is less than equals to, then it is your bitonic sequence. If it is greater than equals to, then also it is a bitonic sequence. So this is a bitonic sequence. What about this one? This is also bitonic sequence because by cyclic shift I can find out this is less than equals to E1 less than equals to up to less than equals to Ej minus n. Right? Then I can get Ej minus n plus 1 greater than Ek minus n, whatever the relationship between this, again less than equals to this, so it becomes a bitonic sequence. So the first part is that D and E, they are bitonic sequence, that is true. Now what you have to show, that maximum of D is less than equals to minimum of D. Now suppose you have a bitonic sequence now, A1, A2, A3, A4, AN. Right? What should be your network? Network will look like that you have comparators, n by 2 comparators, and here you have an by 2 plus 1, an by 2 plus 2, and so on. So it goes like this. Okay, so this is a bitonic sequence. This is a bitonic sequence. So I has to be compared with an plus I. So same thing we did. And then you get n by 2 bitonic sorting, bitonic merging network, and you have n by 2 bitonic merging network. Right? So you get here basically D1, D2, Dn by 2, you get E1, E2, En by 2. Then recursively if you call, you get C1, C2, C3, Cn by 2, you get Cn by 2 plus 1, Cn. Right? So you have by one comparator, AI is compared with An by 2 plus I, smaller elements, you keep it in the D sequence, larger element bring it to E sequence, then recursive, this becomes a bitonic sequence, this becomes a bitonic sequence, recursively you do it, and then finally you get the sorted sequence this side, sorted sequence this side. Right? Now if it is the case, then how many comparators you need? Number of comparators is n by 2 plus Cn by 2, 2 times. If n is greater than 2 and 1 if n equals to 2. N by 2 plus 2n by 2 if n is greater than 2, 1 if n is equals to 2 because you have two elements and you need one comparator. And the number of steps, parallel steps you need, Tn is equals to 1 plus Tn by 2 if n is greater than 2, 1 if n equals to 2. Right? Because 1 and then whatever time you need for doing that. Now assume n is equals to 2 to the power k. So you can easily solve Tn right? Because this becomes T2, T2 is also 1, so it is K, which is your log n. Now if I have to compute Cn, Cn is equals to 2 times Cn by 2 square plus n by 2 square plus n by 2. So you get 2 square Cn by 2 square plus n by 2 plus n by 2. 2 to the power k minus 1 Cn by 2 to the power k minus 1 so 2 to the power k minus 1 because C2 is 1, so you get k minus 1 n by 2, and this is also 1 n by 2, right? So you get k n by 2, that is n by 2 log n. So you got Cn is equals to n by 2 log n, Tn is equals to log n. Cost is n by 2 log square n to merge a bitonic sequence into a sorted sequence. One thing you observe that you must have a bitonic sequence to merge this one. So the sequence must be a bitonic sequence. If I have to think that how can I use this idea to sort an arbitrary element. So let us consider the 8 elements. 7, 1, 2, 4, 3, 6, 5, 8.
Two elements are always bitonic and then
Yes. Idea is that you use the assumption that 2 elements are always bitonic and then you merge it. And you must get it, after merging you must get the largest bitonic sequence. So basically it is nothing but, the idea is that you this one you make it increasing sequence, this one you make it decreasing sequence. So that you get, at the end of this, you get a bitonic sequence of larger size. So here you will be getting 1, 7, 4, 2, 3, 6, 8, 5. So you observe now, this is a bitonic sequence, this is another bitonic sequence. You convert this into a sorted sequence in increasing order. This should be in increasing order. and this should be decreasing order, so that this becomes another bitonic sequence. So in order to do that, this should be in increasing order. You first compare right? AI has to be compared with an plus I. So you get here 1, 4, 2, 7. Now this becomes a bitonic sequence. This becomes a bitonic sequence. So you get a sorted sequence here. Similarly is the case here. So you compare these two, you get 8, you get 3, you get 6, you get 5, and then you compare these two. You get 8, 6, 5, 3. So this is becoming another bitonic sequence. Now you observe, at the end of this stage, you get a bitonic sequence of size 8. Now you have to make it a sorted sequence. So AI has to be compared. That means this has to be compared, this has to be compared with this has to be compared with this, and this has to be compared with this. Right? After doing that, so if I compare 1 with 8, you will get 1 here 8, 2 with 6, 2 here, 6 here, 4 with 5, 4 here, 5 here, 3 with 7, 3 here, 7 here. Now the problem is that this is a bitonic sequence and this is another bitonic sequence, and all these elements is larger than these elements, right? Because DI is smaller than EI. So you now compare this with this, this with this, this with this, and this with this. You get here 1, 4, 2, 3, 5, 8, 6, 7. Then you compare with this. 1, 2, 3, 4, 5, 6, 7, 8. Now, how many parallel steps you need, parallel phases you need? This is phase 1, phase 2, phase 3. So, if you have a bitonic sequence, if you have a sequence of 8 elements, there will be 3 phases. That means you have the log n phases. Agree? And at the ith phase, you have several parts, each of size 2 to the power I, bitonic sequence. At the ith phase, there are log n phases, Agree? At the ith phase, there are several bitonic sequences, each of size 2 to the power I. Now, can you tell me what is this value of several? N? N? N by 2 to the power? N by 2 to the power I. Yes. That is 2 to the power k minus I. N is 2 to the power k. Right? So that many parts are there. In this case, second phase, you have 2 to the power I, 2 to the power 2, 4, and there are 2 such cases. So it is 2 to the power k minus I bitonic subsequences, each of size 2 to the power I. Agreed? Now, if it is the case, so can we find out total number of parallel steps and number of comparators? And then type of comparators. So we need to know these three things. You observe that here it is not like odd even merge, so that comparator has two inputs and the output is, the first output is the minimum and second output is maximum. Here it is depending upon the phase, whether it is in increasing order or decreasing order, right? So there are two types of comparators you will be using, A and B, mean right? Actually, it is not very difficult to implement. First one, if you can implement, only the word you have to change to give you the maximum output in the top and minimum output will be there, nothing else. This is not a big thing. And only thing is that you have to phase wise you have to keep it in mind which comparators you will be going to use. Right? In the first phase, alternatively high low high low high low. Here is second phase, it is low low high high, then it is low 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 low. That is the only thing, right? So there is some easily you can, there is a, so the type of comparators you will be using, that is known to you. Now what about these two? Now number of parallel steps. First phase, 1 parallel steps. Second phase, how many parallel steps? Right? How many parallel steps? This is one, and this is one, and this is another one. Agreed. Third one is what? How many parallel steps? This is one. This number of parallel steps you have already obtained. And the third steps, you have 2 to the power 3 elements. They are bitonic sequence, and you are making 3 parallel steps. At the ith phase, you are making I parallel steps. Agreed? So, I parallel steps at the ith stage. How many I? I is 1 to log n. So it is log n plus 1, which is order log square n. So number of parallel steps is order log square n. Now, can you tell me how to find out the number of comparators? At the ith stage, how many parts are there? 2 to the power I, 2 to the power n minus I. That many subparts are there. In the ith stage, 2 to the power n minus I subparts are there. This is a bitonic sequence, is size 2 to the power I. Agreed? So, this is 2 to the power I minus 1, I. Summation over I equals to 1 to log n. there are n minus 2 to the power n minus I subparts are there. Each part is a size of 2 to the power I, which is a bitonic sequence. To do that, you need the number of comparators I into 2 to the power I minus 1, which has come from here.
2 to the power k minus I.
Or 2 to the power? Yes,
K
it is k minus, yes. 2 to the power k. K minus I, yes. Agreed? If it is that, this becomes summation over y log n 2 to the power k minus 1 I. 2 to the power k minus 1 goes out, and it is I summation over I, which is again log of n plus 1 upon 2, which is ordered n log square n. So you can write number of comparators you need ordered n log square n. Number of parallel steps is ordered log square n. So for sorting n elements, you need the cost is ordered n log to the power 4n. So it is also far away from the cost optimality point of view. Now what should be the basic unit of bitonic? Basic unit will be, suppose you have the four elements and which form a bitonic sequence. Right? That is the two elements you need to give you the sorted sequence. Four elements. If you have four elements which forms a bitonic sequence, the structure is like that. Now, if you have to combine both the things for obtaining a sorted, suppose it's an arbitrary elements and you want to have the sorted sequence, you can easily find out that. This maybe, suppose this is an arbitrary one, A1, A2, A3, A4. So first you make, this is low and this is high. This is high, this is low. Now this becomes a bitonic sequence. Now in the second phase, you get low, low, high, high. So you will get the sorted sequence. Right? Now, if you observe or if you compare this with odd even merge techniques, you will find what? Is the same number of comparators? Sure? Or less number of comparators? Order-wise sequences. But you are using more number of comparators because if you observe, that was if you have an odd even merge, you do the odd even merge netting plus n minus 1. You don't need n comparators. Here you need,
Only 3.
right? So number of comparators is increasing. Cost wise it is of the same order, there is no problem. Moreover, in bitonic merge, you have to keep track odd even, you have to keep low, high, low, all those information, which you do not have to keep for odd even. So this is all about your bitonic sequence. Now, any questions on this? If it's not, then I don't want to start the sorting algorithm.
So what is its gain means?
Gain?
What is gain of bitonic sequence means? What is use?
Oh, it is bitonic sequence. You will realize for network models, we will discuss how efficiently we can use the bitonic sequence to sort an element, which may not be possible on for odd even merge to implement on network models. We will discuss this thing.
In a
Right.
general case, it is not recommendable because number of comparators is greater.
Yes. Not only that number of comparators is greater, it is also you have to keep track with how many of low high, how many high low comparators you need. Right? And could you go through could you get the time to open the book Node volume 3? No. Is there anybody who could see the Node volume 3?
The
No.
one you had asked to check in the library.
Minimum, no. I asked minimum sorting network, minimum number of comparators, that type of chapter is there in Node volume 3. In chapter possibly 5, 5.4 or something like that. You please go through that sorting network discussion is there. Can you use any one of them? See, here you observe what we did. We started with two elements. Instead of that, if I use 5 elements, whether we can achieve the goal of sorting efficiently or not. If it is, by how much? That type of things you can think. Because what we observed, that if the number of elements is odd, the number of comparison takes lesser to sort.